Today, we want to look at the Riemann sum. The Riemann sums. Consider a function like this. Y equals f of x. Let f of x be a continuous function. Defined on a closed interval AB. Our function y equals f of x is defined on the closed interval AB as shown. We use the Riemann sum to approximate the area under the curve. In order to do this, we are going to divide the interval AB. Into n equal subintervals. Such that A is equal to x naught is less than x1 is less than x2, down to n minus 1 to x sub n. This tells us that within the interval AB, we have n subintervals as follows: x0, x1. Let's be guided that these intervals, they are closed and bounded, just as our interval AB. We have n subintervals, x1, x2, down to the last subintervals, x sub n minus 1, xn. The width of each subinterval, which we'll call our delta x, can be gotten as b minus a over n. That's the width of each subinterval. That's our x naught, as we can see on the graph. That's x1, x2, down to our b, which is the xn. Remember, we said that we are going to divide the area under the curve into n equal subintervals. These subintervals, or these short intervals, we call it the partition of interval AB. The partition of interval AB. partition of interval AB. Now, remember that our curve is f of x. At x1, I have a value f of x1. At x2, we have f of x2. Down to at xa, then we will have f of xa. How do we calculate the area of a rectangle? You will remember that the area of a rectangle is calculated as length times breadth. Length times breadth, or length times the width. The height of the rectangle, which is my fx, will be the fx1 times the width. Remember, we have said that we are dividing it into equal subintervals, which tells us that the width of each of the rectangles are the same. So I have this to be approximately equal to fx1 delta x1. That's the width between the first interval, plus fx2 delta x2 plus down to f x sub n delta x sub n. We can write like as the summation of I tends to I from 1 to n of f of xi delta x. That is the Riemann sum to approximate the area under the curve. However, our Riemann sum can be of different types. Our Riemann sum can be of different types. We can have the lower Riemann sum, This most times we make use of the left end points of the interval. We have the upper Riemann sum, which will make use of the right end points, and we have one which you can call the midpoint. This will make use of the midpoint of the interval. Our lower Riemann sum can be denoted as what? As L, the lower sum of f with respect to the partition P, and this is equal to what? The summation from I equals 1 to n of mi into delta x, or delta xi, where my delta xi is what? is my interval xi minus xi minus 1. The width of that interval. That's our lower Riemann sum. And our mi is the infimum of f of x, such that xi minus 1 is less than or equal to x is less than or equal to xi. That's the infimum of fx. And remember we said for a positive function, it most times is the left endpoint. Most times it will be the left endpoint. The upper Riemann sum now, the upper Riemann sum follows the same process. The upper Riemann sum u of f with respect to partition P is equal to the summation as I moves from 1 to n of capital Mi delta xi, where our capital Mi now is the supremum of f of x, such that our xi minus 1 is less than or equal to x less than or equal to xi. Our delta xi still remains the width of the subinterval xi minus xi minus 1. The width of the subinterval xi minus xi minus 1. Riemann sum. We have talked about Riemann sum to be approximately used, or to be used approximately to obtain the area under a given curve by partitioning the curve into n sub-intervals, or the curve into n rectangles. And we have seen how that is done. And we can see our upper Riemann sum and our lower Riemann sum. In the next video, we'll be using this to solve some examples. See you in the next video.